presenting the problem of filling up the bottle. So the problem statement is, when a vertical water jet enters the bottle, sound may be produced, and as the bottle is filled up, the properties of sound may change. Investigate how the relevant parameters of the system, speed, dimensions of the jet, size and shape of the bottle, or the water temperature of the sound. So this presentation is going to be three main parts: the observation part, the parameter investigation, and then finally I'll be concluding. So for our observation part, I'm going to be using an ideal bottle, meaning that there's a clear distinction between the neck and the cavity, as you can see here. So from our setup, we're going to have a nozzle, and we're going to control the flow rate with a motor, our microphone, and finally our bottle. So here's a quick video of the phenomenon. I'm sorry, the sound. You're not able to hear the sound. But as you can see, what you can notice here that to go back to the problem statement, how does the water affect the sound? You can see that the intensity and the frequency of the sound change. However, since the intensity is a secondary parameter, it's not going to be much focus, and we're just going to assume that the intensity is enough to be audible. And for frequency, to analyze it, we're going to use a spectrogram to see how it evolves with time. And this is what we get. From this, we notice a few interesting things. First of which, the data is very noisy in the 4,000 to 8,000 Hz range. Next is that, so from that we're going to turn our focus to the lower temperature, lower frequencies. From that we can see that frequency increases with time. However, we notice something strange in that the frequency just starts to flatten out and goes forward. We're going to concern this at the last part of the presentation. And finally, we observe multiple frequency components. So from this, we're going to visualize the phenomenon from the ground up. At the bottom, it has to do with the sound generation. So when the water hits the water impulse, when you draw the impulse graph, you see somewhat similar to a direct filter function. This is an ideal case. So when you do Fourier analysis, you can find that virtually every frequency is generated. So however, this isn't the only sound making mechanism. Sound can also be produced by the bubble bursting. The popping of the bubble would generate pressure, and that pressure would then create sound, and this would create a specific range of frequency, unlike before. To experiment to verify this, we had our nozzle to range to create bubbles, and our microphone. And this is our experiment. So as you can see, you can only hear sound from the bubble pops, and from when we are doing our spectrogram, we can find that the sound produces in the 4,000 to 8,000 Hz range, meaning that this is what contributes to the noise of our system. Next is the cavity. Moving on from every frequency is generated, however, only a certain amount of frequencies are going to be amplified, and so we're going to hear it. This is going to follow the resonance in a closed tubing. The reason it's a closed tubing is because, one, the water acts as a reflector, and the transition between the cavity and the neck acts as a quasi-closed, and I'll explain. So while it is at the transitional point, while it is an antinode, when the area of the neck is much less than the area of the cavity, we can assume it to be a quasi-closed point. And we will experimentally confirm this later. So moving on to our neck, we're going to use the fact that the neck is much smaller than the wavelength of the sound. So from this, we can model the neck air as a mass instead of a wave. So this is going to, so the air pressure can drive it, and the sound producer is going to follow the Helmholtz resonance, which depends on the cavity volume, area of the neck, and the length of the neck, and we already accounted for in direction. And however, one thing to note is that this model does not predict higher modes of the neck resonance, which we'll get to in the later part of the presentation. So this is by fitting the Helmholtz resonance and the cavity resonance with our observation, and we notice two key things. First is that we notice the higher modes of the neck resonance. This is because the neck of our ideal bottle is around 8 centimeters long, so our assumption there is invalid. And next is that the cavity resonance is off. Now, why is this so? This is because when a wave sound propagates to the transitional point, while some waves goes forward, some waves are reflected back, and this can interfere with the one already in the cavity. So the bottle air, so the variation in the bottle air will modify the cavity resonance. So next we're going to move on to a parameter investigation, and we're going to add the frequency evolution after that. So here we're going to investigate four main parts: the bottle's geometry and the water characteristic. For the bottle geometry, we're going to be doing the bottle shape, neck length and specific, and the water flow rate and the water temperature. So first of all, it's the bottle shape. Here we're going to be using four different bottle shapes, and this is the results that we get for the first, second, third, and fourth bottle. So here's by fitting the Helmholtz resonance and the cavity resonance. For the first one, we can see that the cavity resonance fits very well, verifying that it is a closed M2. And the reason it doesn't need it because the variance of the bottle area is not much. However, this cannot be said for the same for the last three bottles, where both the Helmholtz resonance and cavity resonance deviates from the theory. And one thing to note is that we only see the forced order of the neck resonance, meaning that in real places the bottle neck can be assumed to be very shorter than the wavelength. So why does it deviate from cavity resonance, and why does it deviate from a Helmholtz resonance? The reason it deviates from a cavity resonance is, as before, when the wave propagates, some of it is reflected back due to the geometry of the bottle. And for the Helmholtz resonance, it's because we are violating the assumptions of the Helmholtz resonance. One is that it assumes the pressure in the cavity to be positional invariant. However, this is obviously wrong because our cavity is a standing wave. Next, it assumes a small mass in the neck, so that the oscillation of the mass does not affect the cavity. And finally, it assumes the neck to be shorter compared to the wavelength, so we can assume it to be a mass instead of a wave. So from this, we can see it's a very complex situation. So for a quantitative analysis, we're going to be using COMSOL. First of all, we're going to be tracking the bottle's curvature, fitting a polynomial function, so we can recreate the geometry in COMSOL. And from that, what COMSOL is going to do is going to discretize this bottle system and using a frequency sweep to find what's the resonance frequency for a certain geometry. And to compare the theoretical and experimental, we need to extract the data from the spectrogram. To do that, we're going to use malloc to manually extract the coordinates as such. And because this data is going to be noisy due to human error, we're going to use the Savitsky Goblet filtering to increase the extracted data position. And this is an example of the extracted data. So here's a comparison between the theory and experiment. As you can see, the COMSOL predicts the predictions is very low and only deviates at higher frequency. This is because COMSOL models the bottle by discretizing into elements and assumes that the element is uniform. However, especially at the change in the area, the elements do not need to be uniform. And so, to add on to that, when the frequency is high or the wavelength is low, the variation also increases. And so that COMSOL would start to go at higher frequencies. Next is the neck length. So here we're going to be increasing the neck length and see the results. And this is what we get for 2 centimeters to 10 centimeters. First thing, we're going to compare the 2 centimeters to no neck at all. And what we notice is that for the 2 centimeters that there's a higher mode of the neck resonance, further validating our assumption. And because it starts to become very wavelength. Next, we're going to compare the 2 centimeters to the 10 centimeters. And this is the result that we get. And as you can see, the longer the neck length, the lower the neck resonance frequency is going to be. And this can be explained qualitatively by the Helmholtz resonance. So for quantitative analysis, we used COMSOL, and we find that it predicts the phenomenon very well and only deviates at higher frequencies. Next, we're going to talk about the water flow rate. Here we're going to use 2 different water flow rates and report the results. And this is what we get for the 12.86 and 39.52 centimeters cubic centimeters per second. So we're going to extract the data and compare the first and second harmonic of the 2 cases, and we find that the flow rate only affects how fast the water is filled. And for a quantitative analysis, we plotted with COMSOL and found that it predicts it exceptionally well and only deviates at higher frequencies again. So lastly, we're going to be talking about the water temperature. Here we're going to be using 3 different water temperatures, which we're going to control by using ice. And that's the result that we get. So we're going to compare the first and second harmonic cavity resonance for the 3 temperatures, and we see from the graph that the deviation only towards that there's only deviation towards the end. To explain this, we note that while temperature does affect the speed of sound, this change is not instantaneous. And here's a quick graphic to show why. If you had a water of 10 degrees and a bottle temperature of 26 degrees. When we pour the water in, it takes a while for the air temperature to actually reach thermal equilibrium. And the water is going to be the initiator of the heat transfer mechanism in this case. So in the last part, we're going to be talking about the weird frequency evolution, which you've noticed that the frequency seems to be somewhat hitting each other and going out. This is because we have not modeled the interaction between the neck and cavity in the previous theories. So here we're going to do just that. So let's try to visualize what happens. When our sound wave propagates to the neck length, we see that due to the sudden contraction, the wave is going to expand, causing there to be an effective velocity drop because the energy is going to be spread out. But however, due to the boundaries of the neck, it is going to be corrected. So when we draw the velocity to the distance, this is the graph that we're going to get. And so from this, we're going to use an analogical constraints for our cavity and for our neck, which is a closed and open net, as you can see. So we're going to look at the boundary. What does it mean when the velocity drops? This means that the mathematical length is going to increase, meaning that we can model the boundary as a concentrated point of mass. So from that, we're going to create the wave equation for our cavity and for our neck. From that, we see that there are four variables that we don't know, so we need four boundary conditions. The first boundary condition is going to be, so we're going to use the end boundary conditions and the transitional point boundary conditions. The first one is going to be that the left end has to be a node, and that the right end is going to be an antinode. And for the transitional point, it means that it has to have the same displacement. And lastly, we can find the mass acceleration due to tension. From this, we can solve for the wave number that results in the resonance frequency. As you can see, our model correctly predicts the coupling of the frequencies. As such, the transfer of energy when the frequencies become very close to one another. And one thing to note is that it also correctly predicts the higher modes of the neck resonance, which is what Helmholtz resonance has failed to do. So to conclude, we have found that the sound created is due to two main mechanisms. The water-water impulse, which is the main mechanism of the jam generation, and the bubble popping, which contributes to the noise of the system. And we found that the sound change is due to the change of the resonance in the bottle's cavity, which we've explained, which we've modeled it in three ways. The first one is the resonance in a closed tube for the cavity. We found that this works for simple geometries. The console, which works for complex geometries that have lower frequencies, and the boundary at the transition point, which works for the couple, which can also explain the coupling between each frequencies, and it also fits better at higher frequencies, which can be discussed about if needed. And so we varied four parameters: the bottle geometry, the neck length, the water flow rate, and the water temperature. We found that the bottle geometry changes the resonance. The neck length changes the neck resonance. The water flow rate affects how fast you hear the sound change, and the water temperature only affects when time moves on. That is it. Here's my reference, and that is it for my presentation. Thank you.
Thank you very much. Time for the opponent's questions.
Hello, thank you for your presentation. And now I want to ask you some questions. Do you think intensity is a secondary parameter?
I can elaborate on that more. So I said the intensity is a secondary parameter because it only depends on how hard the water is hitting it. So if you look at the four parameters, the intensity wouldn't be affected as much as the frequency. So that's why I said it was a secondary parameter.
When water hits the bottom of the bottle, is it a noise or no?
So it's going to be similar to the water-water impulse. The impulse is going to be somewhat like a direct delta function. It's not going to be an ideal direct delta function. There's going to be a width to the impulse, but it's going to generate a large scale of the frequencies like the water-water impulse.
What flow did you have?
What flow?
Experience. Mineral turbulent.
Could you repeat the question?
What flow? Did you have laminar or?
Well, it was in the relative stability, so the water started to break out. So I think you can consider it to be turbulent.
Did you test different materials?
Of the bottle? Yeah. Oh, we did not, because that would only affect the initial part, and it wouldn't affect it that much. So we didn't vary that parameter.
I think we got. Do you think that there are other theory models that can explain?
Oh, well, you could improve the model that we created. You could improve on that part to make it more valid, to make the fit theory better. Yes. We could discuss about that.
Okay, thank you.
Okay, it's time for preparation.
Yeah, my name is from Greece, and I'm going to give you a comment in problem number 5. What's the problem presentation? When a vertical body jet enters a bubble, sound may be produced, and not the bubble is filling up, the properties of the sound may change. Investigate how relevant parameters of the system, such as speed, the dimension of the jet, size and shape of the bottle, or water temperature affect the sound. First, we summary of the recorded presentation. about the theory, how these numerical and theoretical models were created. The fact that because the different parameters have on the directions and frequencies was presented. About the experiment, they changed relevant parameters such as temperature, flow, speed, and all sides, produced clear experimental graphs that fit the frequency range. Strong point now about the report was the interactive images. They had audio footage, theoretical explanation, and theoretical explanation were presented. Detailed graphs to present the experimental results. They included an explanation concerning the experimental results, and the reporter answered my questions here now. About the weaknesses now, having judgment is applied to objects that have a narrow mouth, so the air under the body creates sound. They didn't examine a variety of bodies. They did not use different materials to examine the effect that density of the material has to the range of frequencies that are produced. And they stated that 7 parameters are limited unsuitable when they are important. To conclude, it was a good presentation, but I think that there were some other theoretical models that could explain the phenomenon more clearly. And thank you for your attention.
So let's proceed to the discussion now.
So, do you believe that laminar and turbulent flow has a different effect in this particular problem?
Okay, so there would be a difference in a sense that it would affect the sound generating mechanisms, as we said. The water impulse is going to create, the impulse is going to be, the impulse is going to be something similar to a, like something like this. The impulse is going to be like this. The narrower the impulse, the longer the frequency range that's going to be generated. So if it were laminar, because of the way the flow is going to be, it's not the stability of it, it's going to create the impulse to be fairly spread out compared to the turbulent flow, which is going to have more instability. The water droplets are going to affect more. And so this would create, so if we were to use laminar flow, the frequency produced would be a smaller range. However, it isn't that, the range frequency would still be in the range of that frequency still here. So there would be a difference, but we would notice it.
And now about the temperature.
The temperature.
How do you think it will, if you increase, for example, the temperature?
If I increase the temperature, so I'm going to pull up the temperature investigation. Oh, sorry. And from this, you can see that the higher the temperature, I'm sorry, the scales might be hard to see. Here is the top one is 16 degrees Celsius, the bottom one is 11 degrees Celsius. So you can see if it gets higher, it's going to increase the deviation towards the end.
Thank you. Do you think that the bubbles, if when the water flow creates bubbles, it has a significant impact on your...
Well, in our presentation, we said we did an experiment that we also experimentally verified this. Is that the bottle has to do with sound generating mechanisms, which apart from the water impulse, it's also going to create a sound of its own. It is going to create the frequency of its own. However, for our system, we found that it only contributes to the noise of the system for our analogy purposes.
About the other vertical explanation, for example, if you have a cylinder with no neck,
Cylinder with no neck.
how do you think it would happen?
So a cylinder. So could you clarify? Is it the cylinder like this, or is it like a water bottle? You just take out the neck, so there's just a small hole. Is it which one it would be? The top one. So it would be using the simplest explanation, it's going to be a closed and open. Yes.
Because there, I think there is theoretical model from the sandwich.
Yes, that's what we did for our simple geometry, for our simple explanation, was the thing with the resonance. Yes.
Okay.
So you said that in your presentation, you said that the Helmholtz resonance was invalid?
No, I didn't say that. But I said it in some situations, like when you use time waves.
Okay, in addition to that, if you have
Yes, of course. Also, you thought that sound intensity of the suppression has a predictable effect. You should have tested that.
Okay. I partially agree with what you're saying. However, to my defense, is that due to the time limitation, you have to focus on either one. And frequency was much more interesting and is much more predominant in the effect of the sound that we hear. And so that's why I said that's intensity. But yes, we could experimentally verify it as well.
And about the materials, did you test plastic and glass?
Plastic and glass. So we did it when we changed the bottle shape. For the first bottle we used was so the first bottle that we used was plastic, while the other was glass, and there was really no discernible difference between each material of the glass. We could discuss more of it if you want.
Yes, about the comparison between plastic and glass.
Okay, so do you want me to explain how it would be different?
Yes.
Okay, so while I said that there's no major difference that we noticed, the only difference is I'm going to be saying two things. The first one is the sound generating mechanism of it. Would you agree? Because as I said, when it hits, there's going to be an impulse, and the width of this impulse graph is going to be dependent on the material. And so because of that, we're going to change the input frequency of the system. Let's say, however, we're only going to be able to hear the same thing because the change isn't going to be that significant in the range of a human hearing. The second thing that it might affect is the absorptivity. So when the absorptivity happens, if you say that more energy is absorbed by the material or it is lost to the environment, the intensity of it would be less. And so that's how it's toothpaste.
I believe, in my opinion, that in the glass, well, the harmonics, if you do the graph in the same dimension,
Yes.
which one is same, the harmonic you have like the frequency here in hertz time, it would be a clearer graph versus in plastic, where it would be more.
Yes, it depends. Yeah, so it depends on the activity of the sound that you hear. Yes, I would agree. But the effect would still be you wouldn't there won't be a significant difference if you do a spectrogram or if you hear it by ear. So maybe you would like to talk about the coupling of the system, because I think that's a very interesting part of the phenomenon that we found. Would you agree? So do you want me to elaborate more on this part?
Yes.
So first of all, I should explain because I think I wasn't really clear when I just said that this is the coupling of frequencies. So let's visualize what's happening in this one, shall we? So we're going to use the analogy, so we're going to use the string analogy, correct? The mass. So when these are going to resonate with their own frequency resonance, correct? Frequency resonance. This one's going to be for the cavity, and this one's going to be for the neck. So the cavity is going to get shorter and shorter and shorter and shorter because the water is filling up. So the frequency of the resonance is going to change, correct? And when the frequencies are different, we can see that the net acceleration of the mass is going to be little because this is going to pull one way, this is going to pull another way. So this would act as more or less as a boundary, and these two could be considered independent. However, if the frequencies got close, so if we decrease this frequency enough so that these are close to one another, there would be a energy transfer between the systems. And so coupling, so to transfer the energy of the cavity could then be transferred into the neck, which I thought was really interesting because the frequency has coupling, as you can see. Maybe I said in the presentation that this works better at higher frequencies and not lower frequencies. And do you want me to elaborate more on that part as well? Or I could elaborate more on console if you want.
Did you know that you knew the sandwich theory?
Yes, sandwich
theory. So, do you know the equations?
The equation? Yes, so it's going to follow the closed energy equation.
Can you write it in the...
Okay, so I'm going to use a closed end. So this is going to be lambda over 2 of the weight, right? So we can say that lambda over 2 is going to be equal to L, and we know that the velocity equals to the frequency times lambda. So we can multiply this to become
about frequency.
Yeah, so we can get the frequency relationship as V divided by 2L. In this presentation, I use V and speed of sound. So C divided by 2L.
Okay, but here,
Yes, it should end time. But this was for the first time, and yes, that's it.
Did you conduct the experiments about the dimension of the bottle?
It is incorporated into the flow rate, yes. The flow rate is the dimensions times the velocity, area times the velocity. So it is included in the flow rate.
And what did you show?
The results was that it just makes the water go faster, so the sound here very is faster.
Okay, time is over. Let's conclude.
Okay. Thank the reporter for the conversation. I think we had some sort of conversation and we agreed on most of the points, most times in our discussion. And I think that I got a clear view that the reporter understands really well the theoretical model of this problem. But I think he should test sound intensity and he should test the dimension and the speed flow of the water jet separately and not in the same experiment. And thank you all.
Thank you. It's time for the review question.
Okay, my first question is to the reporter. Do the dimensions of the jet affect the resonant frequencies?
The resonance frequency, it can
Yes or no, please?
it does, but it's very little.
Okay, fine. Did you try to change the dimensions of the bottles so that you can test for different resonator theories?
It's the same as changing the flow rate because of the
yes or no? Dimensions of the bottle.
I would say we did not, but it's the same as changing the volume
thank you.
of relative.
What does the opponent think of it? Should this be done? Changing
Yes, I
dimensions of
think
the
it's
bottle. Why?
Because
Could it affect the resonant frequencies? Yes or no?
yes,
Thank you.
uh,
Thank you. What is the cause of the discrepancies at the slide 55?
Slide 55.
It was,
For the coupling one.
yeah.
This one.
The next one.
Okay, so this one, two reasons. First one is that because we modeled the mass very concentrated, meaning the velocity drop is huge. However, in real cases, that's not the case. But at high frequencies, that
Okay,
is
and
more
the
valid.
other reason?
And the other one is that we modeled it as one dimension, so you're losing a lot of information by turning a 3 dimension into 1 dimension.
Okay, nextly on the slide 39.
39.
Did you compare this with the theory?
We didn't have a quantitative model for this one.
Didn't you?
We did not have a
So
quantitative.
this does not affect your theory, you are stating this?
No, it does affect the theory, but we could not because but it is hard
Okay,
to model heat transfer.
for the opponent, where does the temperature enter the theory?
I think in a higher temperature,
Yeah.
they are created more bubbles. So
Okay,
they produce
thank
more
you.
sound.
Do you agree with this?
The temperature does affect the viscosity and maybe the surface tension of the water, but however that change is going to be negligible, especially for the very
Okay,
small.
thank you. Could you show us the spectrograms?
For which one?
For instance, slide 19.
19. Oh, sorry. 19. Yes.
Okay, so we can see the different curves here. Could you comment on to what resonators do these correspond?
So as you stated, as you can see, the black one is the Helmholtz and the red one is the cavity resonance. So
Okay,
you can tell-
thank you. And so what precisely is the cause of this discrepancy?
As we said, it's because of the variations of the water bottle's geometry going to cause reflections inside the water bottle, modifying the actual cavity resonance.
Okay, thank you for your answers.
Okay, time for preparation for you.
I'm going to review the task number 5. At first, I believe we are all familiar with the problem statement. So let us move on to the reporter. Firstly, in the report, the Helmholtz resonator theory was shown. We like this because it allows for the investigation of the whole phenomenon, but we have seen that the reporter does not fully understand this because he stated that the effective area, the dimensions of jet do not affect the phenomena, but they do affect the effective area of the neck, and this enters the Helmholtz theory. They also described the wave function, and which allowed them for the explanation of frequency coupling to explain their fancy frequency graphs, which we liked because it is important, to explain the phenomena. They also correctly stated the effect of temperature, that it has the effect on the transfer of the air, and nextly they presented experimental apparatus that allowed them for controlling the volumetric flow, which is important here. That they were not investigating the amplitude of the signal, which we mostly disliked, and also that they compared. They did not compare their theory for the temperature with the actual measurement, which could be done because the temperature affects directly the speed of sound. That is where it enters the theory. Nextly, for the opponent, he pointed out that the reporter did not examine the parameters of the bottle. We believe this should have been investigated to test for the different models of resonators. It would affect heavily the Helmholtz resonance through the area of the neck and the half-wave theory through the width, through the height of the bottle. Moreover, they pointed differences between laminar and turbulent flow, which would affect the production of bubbles and thus production of the sound. They misunderstood completely the effect of the temperature, because the effect of the temperature, as I previously stated, is in the fact that it affects the speed of sound, and therefore it enters the Helmholtz theory. Also, they missed the dimensions of the jet, which is important in the Helmholtz theory. They were not at all informative, and they did not state any opinions. Also, the clashes of the discussion. They showed graphs at slide 39, and they discussed the effect of the temperature. Opponent presented no opinion at all, while we think that temperature affects the speed of sound, as I stated, and so the graph showed where for very small temperature differences, and thus the differences that they were displaying might have been also due to the measurement error. Also, the opponent was asking about the importance of the material. We don't know why they asked, did not state opinion. Our opinion is that it might affect the background noise. Thank you for your attention.
Okay,
Okay, so I will defend the opponent and go through the review as well. First of all, is the temperature modeling for a quantitative model for our temperature. The reporter said that we could change the speed of sound. However, he's neglecting the fact that the change, as I said in my presentation, the change is not instantaneous, and that's where we ran into problems. Because if you look at the heat source, the heat initiator, as I said in my experimentation, is both the water jet and the water that's already inside the bottle. So you have to model the heat mechanism transfer between by those two to the air inside the water bottle. So that's a very complex analysis, and that's where we ran into problems. And for the fact that we did not vary the parameter to investigate the intensity or the amplitude. So because of the time limit, we had to prioritize what parameters to consider. And since the frequency is the most interesting one, we feel that we are valid in limiting our focus, our scope, to what is interesting, which is the frequency. And for the jet dimension, we already included that. We didn't include that, which was our mistake. We did not include that into our presentation. But we did take the water jet into the account in the fact that it changes the volume bit. So the volume that we put into our equation was the volume of the actual bottle minus the volume of the water jet. And for our explanation, we feel that we have very fulfilled this part because we provided a simple explanation to what is happening, which is the resonance. And then we provided a more elaborate and more physical explanation, which was our string model, which we used for the analogy to strings. And however, we found that due to the complexities of our system, due to the variations and the reflections and interference of the noise inside the cavity, we could not correctly predict it. So we had to use COMSOL as a complete, however complex solution. So that's it for my summarizing. Thank you for your time.
thank you so much. It's time for jury questions. Please.
The reporter, you talked about a quasi-closed neck. Can you explain quickly what you mean by this?
So do you want me to go to the slide because I think it might be easier if you understand the slide. Okay. So sorry.
What's the term mean?
So it's close because the water. So the water. So are you talking about this one? Am I correct? Okay. So the water is going to be closed then because I think this one is obvious because it's going to act as a reflector. However, it's not going to be an ideal reflector, which is going to cause some discrepancies. But I think what's more interesting is the neck, the transitional point between the cavity and the neck. It's going to be quasi-closed. Sorry, it's going to be quasi-closed when the air from the neck and the cavity is.
What does quasi-closed mean?
So it's going to be an antinode. However, if it's
Thank you.
Yes.
Okay, further questions, please.
Can someone just briefly explain what kind of physics does this magical thing COMSOL do?
Oh, okay. So a COMSOL, you could choose the physics, and in this case, we're going to use it models the way it models it. It models it as a circuit. So you have the cavity, which is going to be the capacitor, and the neck, which is going to be the inductance. and you have loss, which is going to be your resistivity. And it uses that model to model the resonance frequency for each geometry. Yes, that's the physics we use in the console.
Yazis, do you have any opinion on that?
Well, I'm not familiar with this simulation program, but I believe that if it is carefully, if the simulation is carefully done and the model is carefully chosen, then yes, it could be applicable.
Maybe you can repeat for her.
Basically, what does console do? The simulation that I use in my presentation. So if I could add just a little bit more, the console is already a fully functioning physics one, unlike MATLAB or mathematics, where we have to put in their own physics. So for a console, you should be careful just to put in their own boundary conditions in the input to get the correct output.
Okay, any further questions? Gabor?
So the question is,
Yeah.
here, why we
So,
don't
sorry.
have...
You would like to
About the console.
Okay,
So this is not the method that we use in our experiments. We're familiar with other methods. So console is just another method of performing this experiment.
Okay, thank you. So, Gabor, go
Okay,
ahead.
and what about the standing waves into the other direction?
At the neck or at the cavity?
No, so you investigate here the horizontal,
Yes.
what about the verticals? Yes.
So in this part, there's going to be neck cavity in this part. However, it's not going to come out, so we can't hear it. So we only hear the one coming out in the vertical direction. The horizontal is there, but we don't hear it.
Go
And
ahead.
have you seen any decreased line in the spectrogram where the frequency is decreasing in time?
In our spectrograms, we haven't seen it.
Maybe on 19,
19?
the bottom right, in the beginning.
Bottom
Maybe
right.
it's only an optical illusion from here. Yes.
Sorry, which one?
Yeah, bottom right and the beginning left, maybe it's an optical illusion from here.
Oh, yes, this one. We believe it has to do with the reverberation of the system. Sorry,
I don't
completely forgot. The reverberation of the system, where the frequency starts stepping
Vibration of
down.
which system?
Of the bottom.
And what about the reviewer?
Well, I'm not entirely sure because the data representation is quite messy here, and it might.
Oh, okay, thank you very much.
And anything.
Okay.
And might also be
Oh, it was enough for me. Okay.
Could you turn off the light? Maybe you can see it better.
Yes, so there it is. Yes, so sorry, I actually forgot. I was thinking about the cavity resonance if it decreases. But yes, there was a resonance, the reverberation that our system.
Yeah. Okay. Let's go back to light. Then, further questions of jury? If not, thanks again the presenters. So, like usual, we will start with the reporter. Please show the grades for the reporter. It's 9, 10, 7, 8, and 7.
Thank you.
Let's proceed to the opponent. We have for the opponent 4, 2, 5, 3, and 2. And for the reviewer, we have 7, 7, 7, 6, and 6. Okay. May I have this? Thank you. So, let us talk about the grades. We have 10 for the reporter. Paul, please explain yourself.
Okay. Yeah, I think I've seen a lot of, in this competition, problem 5, and I thought this was like an order of magnitude better than everything I've seen so far. So I know there's some points which perhaps can be improved. The only thing I didn't particularly like was the idea that you use COMSOL as a black box and you did not explain further the physics which COMSOL solves. Yeah. The other thing I liked very much was that during the discussion with the opponent, when she runs out of things to do, you suggested things to discuss. So I thought I've taken some marks from her and given it to you as well.
Okay, so maybe Gabor, elaborate your 7, please.
Yes, I give 7. It's also a very good point for me. So it was a great presentation, and you were also very dominating with your opponent. And for me, the only missing part that I can follow your theory. It was very fast for me, so it was only my problem.
Okay, any further comments on that?
I like this report also, and I appreciate your combination of simulation with the theory, but still, for me to study the sound was a little bit wider problem, so you had to study also the amplitude, the loudness, and other frequencies. So in this problem, you can find a lot of effects. So for me to narrow this problem was not so good.
Okay, Zakar, could you, let's say, smoothly proceed to your opponent, because you gave 5?
Yeah, it's not very high mark again, but still I saw in your questions some important topics. You could elaborate on that more, and I saw the potential in that question, so that was good, but still you couldn't find a way to do this conversation between you two a bit more interesting, so that was the problem.
Okay, so what about your 2, Paul? Can you comment on that?
Yeah, I would have given a bit higher, but I took some of your marks. Yeah, so I agree that there are some good points, but they were not followed up. So for example, when you talk about the material of the bottle, and they obviously have not investigated it in detail, but it's obvious that they did not investigate it in detail because they thought it's related to the amplitude. So if you could have brought out the point like he did, that the amplitude is something also interesting to investigate and brought that further, I think it would have been a good point. But if you just left it hanging, then it doesn't mean much. Yeah.
Maybe I also will comment because I gave a 4, which is because I really like your discussion with I really wanted to focus on a certain physical quantities of that model, and that was something I appreciated. The problem arises. I will give you 5 because that was a matter of my half point. But during the questioning at the end from the jury, you should answer questions in a more precise and you have to make your point clear, and this is why it's so. Okay, let's proceed to the reviewer, and maybe I will keep talking. I gave you 7, and then it could be even better. But I discovered that when we're talking about the temperature, you did not really notice that they have investigated only a very small range of the temperature. Because they started with 14 or 11 degrees, and then the last point were 17. So that's like, very small range. If you will elaborate on that even more, you could find 1 point more from me. But still, I was among those 3 judges that gave you 7. So maybe we can ask Susan to explain her 6.
I thought you did a good, solid review, but nothing really that special on it. And your opinions of the analysis was a bit rushed at the end, and I thought that was a shame. So I pulled you down on that mark.
Okay, and then maybe at the end I will comment the situation that, when I'm asking all the teams whether they are ready, you have to give me the chance to realize that she was the one who will oppose it. You asked me that there is some issue, and I told you I will wait until she comes back. And then we were about to start, and I asked you whether you are all ready. And you did not give me a chance to realize that you are not ready. So I make my point very clear. If that, you will wait for her until she comes back. And that's something you have to consider for the future. I wasn't realized that she is going to be a real voter. So she comes later, so it could affect her performance. So be aware that judges are asking you to give them a chance to do it in the most appropriate way. Okay, so thank you so much. We again have 5 minutes break, so be ready 25 to 11.